Welcome to the new video titled Operations with File. Let's start with counting all words in a file. Let's take a look at the entire code example. This is one of the easiest codes. Here, we will define a one-liner function that counts the words from an input buffer and let the user choose where the input buffer reads from. Now we will understand the code. Let's include all the necessary headers first and declare that we use the standard namespace. Our word count function accepts an input stream, for example, cin. It creates an input iterator, which tokenizes the strings out of the stream and then feeds them to the distance function. The distance parameter accepts two iterators as arguments and tries to determine how many incrementing steps are needed in order to get from one iterator position to the other. For random access iterators, this is simple because they implement the mathematical difference operation subtraction. Such iterators can be subtracted from each other like pointers. An iStream iterator, however, is a forward iterator and must be advanced until it equals the end iterator. Eventually, the number of steps needed is the number of words. In our main function, we let the user choose if the input stream will be cin or an input file. If the user launches the program in the shell together with a file name, then we obtain that file name from the argv1 command line parameter array and open it in order to feed the new input file stream into word count. Otherwise, else condition is executed. If the user launched the program without any parameters, we assume that the input comes from standard input. That's already it, so we just print the number of words we saved in the variable wc. Now let's compile and execute our program. Go to the terminal, type in the command for compiling the code. After the successful compilation, let's execute it. Before that, we will feed the program with the standard input without any file parameters. So let's type echo, in double quotes type in foo bar and baz, followed by pipe operator and the command to execute the code. We can either pipe an echo call with some words into it, or launch the program and enter some words from the keyboard. In the latter case, we can stop the input by pressing Ctrl+D. Superb! Here is the required output. We have obtained the word count as 3. Now again use the command /a.out, followed by the program name to execute. When launching the program with its source code file as input, it will count how many words it consists of. So, after executing the file, we get the output, or say the word count, as 61 words. Next, we will be formatting your output with IOStream manipulators. Let's take a look at the entire code example. So go to the Atom editor, then click on the ex6 directory, and inside that, click on the formatting.cpp file. This is the entire code. Here, we will print numbers with wildly varying format settings in order to get familiar with I/O manipulators. Let's understand the code. First, we include all the necessary headers and declare that we use the standard namespace by default. Next, we define a helper function that prints a single integer value with different styles. It accepts a padding width and a filling character for padding, which is set to space by default. With setW, we can set the minimum number of characters output for printing a number. If we print 123 with a width of 6, for example, we get 123. We can control on which side the padding occurs with left, right, and internal. When printing numbers in the decimal form, internal looks identical to right. But if we print the value 0 into 1, for example, with a width of 6, and with internal, we get 0 into space 6. The setFill manipulator defines the character that will be used for padding. We will try different styles. Now let's have a look at the main function. In the main function, we start using the function we just implemented. At first, we print the value with a width of 15. We do this twice, but the second time we use the underscore character for padding. Afterward, we print the value OX123 ABC with the same width as before. However, before doing this, we apply hex and show base to tell the output stream object cout that it should print numbers in the hexadecimal format and that it should prepend 0x to them, so that it is obvious that they are going to be interpreted as hex. We can do the same with oct, which tells cout to use the octal system for printing numbers. The show base is still active, so 0 will be prepended to every printed number. With hex and uppercase, we get the x in 0x printed uppercase. The ABC in OX123ABC is also uppercased. If we want to print 100 in the decimal format again, we have to remember that we switched the stream to hex before. By using dec, we can put it back to normal. We can also configure how Boolean values are printed. By default, true is printed as 1 and false as 0. With bool alpha, we can set it to a text representation. Let's have a look at floating point variables of the float and double types. If we print a number such as 12.3, it is printed as 12.3 of course. If we have a number such as 12.0, the output stream will just drop the decimal point, which we can change with showPoint. Using this, the decimal point is always displayed. The representation of a floating point number can be scientific or fixed. Scientific means that the number is normalized to such a form that the first digit is the only digit before the decimal point, and then the exponent is printed, which is needed to multiply the number back to its actual size. For example, the value 300.0 would be printed as 3.0e2, because 300 equals 3.0 into 10 raised to 2. Fixed reverts back to the normal decimal point notation. Apart from the notation, we can also decide with what precision a floating point number is printed. Let's create a very small value and print it with 10 digits after the decimal point, and once with just 1 digit after the decimal point with the help of setPrecision function. Now let's compile and execute our program. Go to the terminal, navigate to the ex6 directory. Next, we will clear the screen using the reset command. After that, type in the command for compiling the code. After the successful compilation, let's execute it. Nice! Here is the required output. This output is lengthy. The first 4 blocks are from the print helper function that tampered around with the setW and left-right internal modifiers. Afterwards, we played with the casing of base representations, Boolean representation, and floating point formatting. It is a good idea to play with each of these to get familiar with them. Finally, we will be initializing complex objects from file output. Let's take a look at the code example. So go to the Atom editor, then click on the ex7 directory, and inside that, click on the respective .cpp file. I have highlighted the entire code for you. Just have a look at it. Here, we'll define a custom data structure and provide facilities to read such items from input streams as standard input. Let's understand our code. We need to include some headers first, and for comfort, we declare that we use the standard namespace by default. As a complex object example, we define a city structure. A city shall have a name, a population count, and geographic coordinates. In order to be able to read such a city from a serial input stream, we need to overload the stream function operator. In this operator, we first skip all the leading whitespace with WS because we do not want whitespace to pollute the city name. Then we read a whole line of text input. This implies that in the input file, there is a whole text line only carrying the name of a city object. Then, after a new line character, a whitespace-separated list of numbers follows, indicating the population, the geographic latitude, and the longitude. In our main function, we create a vector that can hold a range of city items. We fill it using copy. The input of the copy call is an iStream iterator range. By giving it the city struct type as a template parameter, it will use the operator function overload, which we just implemented. In order to see whether our city parsing went right, we print what we got in the list. The I/O formatting, left operator set W15, leads to the city name being filled with whitespace, so we get our output in a nicely readable form. Next, we will include the text file from which we will feed our program. It looks like this. There are 4 example cities with their population count and geographical coordinates, like Berlin with a population count as 4 million. And these are its coordinates. Now we will compile and execute the code and check what output it yields. Go to the terminal, navigate to the directory ex7. Next, we will clear the screen using the reset command. After that, type in the command for compiling the code. After the successful compilation, let's execute it. Before that, we will concatenate it. Type in this cat cities.txt, followed by pipe operator and executing command. Excellent! Here is the expected output. Try to tamper around with the input file by adding some unnecessary white space before the city names in order to see how it gets filtered out. So here we are at the end of this video. In the next video, we will be playing around with iterators.